Right now, we're watching a pattern that started out as a fairly typical mid-July setup and has, over just the last few days, started escalating fast into something that's going to touch almost every corner of the country before the week is out. It's Sunday, July 12th, and between the storms rolling through the south today, a heat dome that's about to expand and shift east, and a Tuesday severe threat lighting up New England, there's a lot to get through. So let's dig in. Let's start with what's happening today. There's a slight risk of severe weather, a level 2 out of 5, stretched from Louisiana up through Mississippi and Alabama, and farther east into Georgia and the Carolinas. This is the tail end of a pattern that's been repeating for days now, storms training over some of the same ground again and again, and the Storm Prediction Center has been watching it closely because even when the wind and hail threat is only moderate, the flooding threat from repeat rounds of rain is not something to shrug off. If you're anywhere in that zone today, the biggest individual hazard, honestly, isn't going to be hail or even damaging wind, it's lightning. It doesn't take a fully severe thunderstorm to produce a dangerous strike, and if you're outside this afternoon and you hear thunder, that's already close enough to get you moving indoors. Now here's where it gets interesting, because this southern storm activity is really just the leading edge of a much bigger story that's building across the entire middle of the country. There's a broad and unusually strong ridge of high pressure that's currently centered over the Intermountain West, and through the coming week it's forecast to expand and strengthen, stretching from the Rockies through the northern plains and into the Midwest. When a ridge like this sets up and holds in place, it acts almost like a lid clamped over the atmosphere below it, and everything underneath just cooks. We're already looking at a significant and genuinely dangerous heat wave building across the north-central United States, and by the time we get into the back half of next week, some of the guidance is showing heat index values pushing past 100 degrees from the northern plains down into the upper Mississippi Valley, with the Climate Prediction Center flagging a high risk of extreme heat for parts of that region specifically, because the thresholds for what counts as dangerous heat are lower up there than they are farther south. People in Fargo or Bismarck or the Twin Cities aren't built for 100 plus heat index days the way folks in Texas are, and that's exactly why this particular heat wave has forecasters concerned. At the same time, this ridge is building and strengthening. It's also going to start sliding east, and that's the part that turns this from a regional heat story into something that touches 30 or 40 million more people. As high pressure aloft shifts toward the mid-Atlantic, we're going to see hot, humid air get pulled up into Washington, Baltimore, Philadelphia, and the rest of the I-95 corridor by the middle of the week. Some of the latest forecast data is already showing highs pushing into the mid to upper 90s for DC and Baltimore by Tuesday and Wednesday, with dew points climbing into the mid to upper 60s, which is exactly the kind of moisture load that turns a hot day into a heat index nudging up near 100 degrees. If you've got outdoor plans in that corridor midweek, especially anything involving physical activity in the afternoon, this is the kind of heat where you want to front load your plans for the morning and just avoid being outside for extended periods once you get into that 2 to 6 p.m. window. Here's the piece of this that's actually escalating the fastest, though. As that ridge shifts and expands eastward, it's setting up a textbook northwest flow pattern on its northern and eastern flank. And that's exactly the kind of setup that tends to fire off clusters of strong to severe thunderstorms diving south and east out of Canada. We're already seeing that play out for Tuesday, when a disturbance dropping down out of Canada is expected to sweep into northern New England and touch off thunderstorms capable of damaging wind gusts. The storm. Prediction Center has already put a level 2 out of 5 risk on the map for far northern New York, Vermont, New Hampshire, and much of Maine. And the timing looks like storms developing during the afternoon and continuing into the overnight hours before pushing east. If you're anywhere from the Adirondacks over toward Bangor, Tuesday is a day to actually check the forecast again the morning of, because this kind of northwest flow setup can be tricky to pin down until you're within a day or two of it. And that Tuesday threat is really just the first domino, because once that ridge is fully shifted east and centered more over the central and southern plains, the pattern flips into one where the west starts drying out and heating up even further, and the moisture gets squeezed out along the ridge's southern edge. We're already seeing that show up in the extended data, with elevated chances for heavy rain and flash flooding building across western and central Texas, and a slight risk of excessive rainfall already posted for parts of the central Gulf Coast. On top of that, monsoonal moisture is increasing across the southwest and the Four Corners region, which usually means a mix of much-needed rain, but also the classic monsoon hazards, sudden downpours, flash flooding in normally dry washes, and dry lightning that can spark new wildfires in areas that haven't seen rain in weeks. So if you're out in Arizona, New Mexico, or southern Utah, keep an eye on the sky, even on days that start out clear, because this time of year, those storms can build fast in the afternoon. Let's stick with the south for one more second, because there's a pattern within the pattern worth understanding. When storms keep firing in roughly the same corridor day after day, it usually means the boundary responsible for triggering them, in this case a stalled frontal zone, just isn't going anywhere fast. That's exactly the setup we've had for about a week now, and it's the reason forecasters keep drawing similar looking risk areas across the same stretch of the southeast day after day, instead of the threat clearing out and moving on like a normal summer disturbance would. The good news is that these aren't widespread severe outbreaks with a lot of tornado potential. The bad news is that a slow-moving repeating setup like this is almost custom built to produce flash flooding, because it's giving the same handful of counties multiple direct hits instead of spreading the rain out over a wider area. Parkfield matters for a bigger reason than its own history, though. It sits at a transition point on the fault between the locked southern segment that stores stress for centuries at a time and produces large, infrequent ruptures, and a northern segment that creeps, meaning it moves almost continuously in small increments without building up the same kind of stress. Because of that position, changes in Parkfield's behavior can offer scientists a real-time window into how stress is shifting along the broader fault system, even though a moderate Parkfield-sized earthquake by itself would not be the catastrophic event associated with the fully locked southern segment. Given everything we've just covered, it's worth directly addressing the most persistent and most inaccurate idea about the San Andreas Fault: the notion that California will eventually break off and fall into the ocean. It won't, and understanding why actually clarifies what kind of hazard this really is. The San Andreas is a strike-slip fault, which means the primary motion is horizontal, not vertical. The Pacific Plate, which includes the section of California west of the fault, including Los Angeles, is sliding northwest relative to the North American Plate, which includes San Francisco. Over geological time, that means Los Angeles is very slowly moving towards San Francisco, not out to sea. There's no physical mechanism in this kind of fault system for a chunk of the continent to detach and sink beneath the ocean. The plates are sliding past one another, not pulling apart, or one diving beneath the other the way they do at a subduction zone. It's also worth correcting the idea that the fault is a single, clean crack running through the Earth. It isn't. As we've seen at Palmdale and San Bernardino, the San Andreas is better described as a fault zone, a wide, often mile across band of crushed rock, parallel fractures, and splintered strands rather than one tidy line. That's a big part of why cities built directly on or near it face such elevated risk. They aren't just close to a hazard, they're often built within it. There are also physical limits to how large a San Andreas earthquake can get, and they matter for keeping expectations grounded in reality. The fault extends to a depth of only about 10 to 12 miles, and even though its full length runs roughly 800 miles, the physical characteristics of this particular fault system place a ceiling on the maximum credible. Earthquake at somewhere around magnitude 8.2 to 8.3. That's still an enormous, genuinely devastating earthquake, capable of releasing dozens of times more energy than the 1994 Northridge quake, and reshaping large parts of Southern California in a matter of minutes. But it is meaningfully different from the kind of magnitude 9 megathrust earthquake produced by a subduction zone, like the one that struck Japan in 2011. The San Andreas, by its own geometry, physically cannot produce an earthquake in that class. The fault's name itself comes from a somewhat quieter piece of history. Geology professor Andrew Lawson mapped and named the fault in the 1890s, and it draws its name from the San Andreas Lake, a small body of water located just south of San Francisco. That lake exists precisely because of the same kind of processes we saw at Desert Hot Springs, grinding fault motion, pulverizing rock into impermeable clay, creating natural depressions where water collects, forming a string of small lakes that trace the fault line itself. When the fault ruptured catastrophically in 1906, it tore along roughly 296 miles of that northern segment, and the destruction in San Francisco that followed came not only from the shaking itself, but from the fires that broke out afterward, worsened by ruptured water mains that left firefighters without an adequate way to fight the flames. That specific combination, violent shaking followed by fires that can't be properly fought because the water system has failed, is exactly the scenario modelers point to when they discuss what could happen in a place like San Bernardino today. Pulling all of this together, the picture that emerges isn't really about Los Angeles or San Francisco as media shorthand for California earthquake risk, even though both cities do face real exposure. It's about a set of smaller communities built directly along, or in some cases directly on top of, the fault's most active and unstable stretches. San Bernardino, sitting over ground that can liquefy beneath hospitals and government buildings. Palmdale, cut cleanly through by a highway that exposes the fault's violent geologic history and would face significant lateral ground displacement in a major rupture. Cajun Pass, a single narrow corridor carrying an outsized share of the region's transportation and energy infrastructure, directly over a junction where two major faults meet, and where research increasingly suggests a rupture on one could trigger a rupture on the other. Desert hot springs, a city whose entire identity is built on a geological feature that could just as easily turn against it. And Parkfield, the fault segment that ruptures, often enough to be studied in real time, offering scientists a rare, ongoing look at how the broader system is behaving. None of this means a catastrophic earthquake is scheduled for a specific date, and it's important to be honest about that distinction. Earthquake science, even at its most advanced, cannot currently predict the day, month, or even year a specific major rupture will occur. What it can do, and what the research behind Shakeout, Cajun Pass multi-fault studies, and decades of Parkfield monitoring collectively demonstrate, is identify where the risk is concentrated, how bad a plausible worst-case scenario could be, and which specific pieces of infrastructure and which specific communities sit most directly in harm's way. The San Andreas Fault is not a distant, abstract hazard. It's a physical feature running directly beneath the homes, hospitals, highways, and water systems of millions of people, and the communities built closest to it, the ones rarely mentioned when the national conversation turns to California earthquakes, are the ones that would bear the earliest and most direct impact whenever the next major rupture does come.